Okay, so getting onto the assignment guides now, I'm going to talk through fission, fusion and the brachytherapy. So starting with fission, there's two different questions about fission. One's about the waste and the other is about the control rods. Okay, so if you're looking at the topic that involves the waste, so radioactive waste from fission is a problem. Okay, now the reason is often the fuel and the waste products have long half-lives. Okay, that means that it takes a long time for half of the sample to break down. So let's say that you had 1,000 kilograms of waste and it takes, we call it T half, that's the half-life. Let's just say it's 500,000 years. That means after that time, after 500,000 years has elapsed, you've got 500 kilograms left. And then after another 500,000 years, then you've got 250 grams left. Kilograms. Okay, so the time it takes for the sample to cut down to half of what it was takes 500,000 years, no matter what the starting amount is. So again, to go from 250 down to 125 kilos is of course 500,000 years. So this is one of the issues. These waste products have long half-lives, and during they emit radiation. Could be alpha, beta or gamma, depending on what your reaction is, and these can be harmful or fairly harmless depending on which ones they are and where they're released. So again, you need to look up what's going on with your reaction itself. So you might do some calculations with this kind of formula. Okay, so you might look up, that's the decay equation. You'll have a negative sign because it's, breaking down. But that's up to you. You guys would have done Maths B last year, so I won't teach that directly. But that's a good way to do some calculations to model just how much of a problem it is to just, leave the waste hanging around. How long it's going to be, doing bad stuff, I suppose. So there's the one thing to look at if you've chosen the waste products. Okay, what if you chose control rods? Well, control rods, they absorb the excess neutrons in uranium fission. So let's just say you've got, you might look up how much energy each released neutron has, and see if the bonds between the atoms of the control rods can handle this energy. That's the principal operation of the control rods. They absorb the energy of these excess neutrons in uranium fission. And if they can't do that, then you're in danger of having a meltdown. This, unchecked chain reaction of uranium atoms releasing neutrons and, stimulating the breakdown of further uranium atoms or nuclei. So this is the real issue. So, for example, let's just say you had This is your control rod. We can zoom in and look at what it's made of. Some control rods are made of carbon, so maybe they're carbon atoms. So you've got to look up what's the energy required to break a bond between two neighbouring carbon atoms. What type of bonds are they? Are they single bonds, double bonds, triple bonds? In a control rod made of carbon. Okay, maybe it's made of something else that you need to find out what's its bond energy. So, that means the energy required to break the bonds. And then what's the ramifications? What if you do break the bonds between these carbon atoms? What would happen? Would it damage the controller? Would it change shape? Would it make it less effective? What's the consequence of these neutrons flying in with kinetic energy and potentially damaging the surface of these control rods? That's your job to research, as your one thing to look up if you've chosen the control rods topic. Fusion. Well, the easiest thing it's not easy, but the most obvious thing to look up is the claim is we need extreme temperatures for fusion. So why is that? Well, I can give you a clue. I mean, if you're trying to fuse these two things to make this, hydrogen plus hydrogen makes helium. Well, fat chance of getting these two together very easily, because there's that electromagnetic force pushing each other apart. You need to get close enough to, let's grab this actually, include it for this. So there's a lot of repulsive force between these protons, but once you get in this sweet spot here, between there and say here, so basically when you get in between 1 to 2 femtometers apart, you can guarantee that you're going to have enough strong nuclear force to counteract the electromagnetic repulsive force. So that's your goal. Get these two oppositely charged nuclei within, say, 1.5 femtometers of each other. If you do that, you're golden. You'll have enough attractive force to overcome the repulsion, but that's going to take an enormous amount of kinetic energy. Okay, so huge kinetic energy, because what will happen, the kinetic energy we convert it into potential energy. Okay, and we have a formula, electrical potential energy. We know what that is. That's KQQ on D. So basically, if you work out a reasonable distance, you've got that. Two charges, well, you know what the charges of this and this is, because they're just one proton each. And you can look up what that charge is. That's done. That's the potential energy to get them to within that distance. Okay? So you know that. So therefore you know what kinetic energy they needed originally. And then you can look up how kinetic energy of molecules are related to the temperature, because actually kinetic energy is proportional to temperature. And you can go ahead and look that up. Then you might find a claim from some source what the temperature required for fusion is and compare it to what you calculated it to be. And that'd be a great way to demonstrate your understanding of what's required for fusion. Last one, so for cancer treatments, brachytherapy. So for this one, it's very much like the control rod situation. We've got, say examples, cesium-131 or cesium-137, doesn't matter which isotope you find. You can see what it decays down to. You then might use the mass defect formula that we learnt in class in week 1. That process, you can find the joules per kilogram required. Just find the joules per kilogram. Okay. Then you might think, okay, well, how much energy do I need to break bonds in a cancer cell? What does this energy use for? Is it to break DNA bonds, so to disrupt the ability of those cancer cells to reproduce? What is this energy used for in cancer? That's up for you to find out. And so if you find some values, for example, you might find that it's used to break apart DNA. You can find the average energy required to break bonds in DNA, and then go from there, because you've got energy in the substance, energy in the bonds. See how much tumour can be broken down per kilo, which would be excessive, because in medical terms they use fractions of a gram of, say, cesium-137. So maybe change it to joules per gram or something to make it a bit closer to being realistic, and see how many bonds you can break in a cancer cell. Okay, and so that'll be something really good to explore, to show that we can harness the energy from cesium. Another thing to think about is what kind of radiation does it give off. Does it give alpha, beta, or gamma? So for example, alpha particles, they can't travel very far. So if yours gives off alpha particles, you might be very limited to the type of cancers you can treat or how big they are. Because if you've got a pellet next to a tumour and it can only send radiation out that far, well, it's going to be useless. You might destroy this section of the tumour and the rest of it's fine. Whereas beta particles, they can penetrate much, much better. But they're not as good at breaking bonds. Each beta particle doesn't have as much energy as each alpha particle. So it seems quite simple initially just to work out the joules per kilogram of cesium, but once you connect it to what its actual job is, it's not as easy. There's a bit more to explore there, a bit more depth. Okay, so there are the topics. I would definitely have a close look at the Exemplar, because it goes through everything you need to do. It's got comments that you should read through carefully. Okay, and importantly, it also gives you some guidance. Like, you can literally use this graph and this one as well in your report. I mean, a lot of this stuff you can sort of use as well, except this is for Americium, but this is all just introductory stuff. It doesn't really give you much credit, but all these questions linked here give you some clues about how you might analyse each graph, and that's directly going to your assignment. So everyone's assignment will be pretty similar up until this point where we start talking about your specific application. So everyone needs to talk about what makes a nucleus stable by referring to these two forces, the repulsive force and the attractive force. Everyone needs to go into some analysis of this binding energy graph, which shows that some nuclei are more stable than others, and that's the whole reason why we have nuclear energy released. Like, if you go from being a less stable to a more stable, you're going to release your energy. Okay, and that's the whole fundamental principle of nuclear energy. So everyone's going to have something similar for this section. It just depends on how well you do it, how detailed and depth of understanding you demonstrate. And then of course you're going to have I've got 3 paragraphs about my particular specific topic, so you'll have about the same. Of course you'll need, you don't have to include this table in your appendix. I did because I used it, but here's good stuff, like all my calculations for each section. Okay, so you can have a good look through those. Some of those might actually be relevant for your topic as well. So yeah, good luck.